Ladies and gentlemen, recording has started.
Yay!
So, first things first. Before we get into the business of today, calendar. On Tuesday, you took your quiz, and I believe I gave that quiz back to you yesterday. Is that correct? Mm-hmm. Good. So you got your yesterday quiz. Then on Thursday, we finished up the outline dealing with current and resistance. We talked about Ohm's law. And then the second half of the period yesterday, we went down to the library and you started working on your circuits, and a lot of you got good ways. Some of you may not get all the way done. That's okay. We'll talk about them more today. Today, we'll do the outline related to circuits, hopefully making sense of a lot of the things that you saw yesterday, hopefully seeing a lot of the things you saw yesterday again, and make sure that we understand why those things are happening. Okay? Next week, Monday, wrapping up and review. Tuesday, test. Objective sheet is posted. So if you probably be a good idea this weekend to get a copy of that, start looking for some things, making sure you're understanding some stuff. If you have questions, we will answer them on Monday. Okay? Good there as far as the calendar goes. Okay. All right. Yesterday, we started building circuits in the virtual circuit constructor, or whatever this thing's called. Circuit construction lab, DC only. Okay? Based on the information that we talked about before, something we talked about yesterday was current. What is our definition of current, or what is current? Explain current to me. Far ahead. Basically, those electrons are doing what, Farah? More simply, they're moving, right? So we're talking about moving electrons. That's what a circuit is based off of. A circuit is based off of moving charges. So, in order to build a circuit, we got to have a couple things. You all right?
Yes, we're good. I don't even know where the cap is.
Just recapping, Becca spilled her water.
Oh my god.
Thanks for clarifying. Okay.
Thanks.
I get it,
All right.
recapping.
So,
Another recapping the water. Because I bite my nails.
Were you filing your nails?
Yes. Yeah. Okay. Well, I bite my nails and I'm trying to stop, and so I have a nail file. And
Becca was filing her nails. Becca filed her nails and spilt the water due to the nail filing. Because I bite my nails and I'm trying to stop. Quote, she bites her nails.
all right. So, hey, come on, let's go. We gotta get this done, especially because you guys are being recorded. All the other classes are counting on you.
Wait, are they going to listen to this?
Well, I mean, I don't record everybody's class. I just record one a day. So.
Alright, well.
Or one a day, so like if they want to look online, they can find it.
All right.
I'll tell Scotty to listen to it. Continue.
So, a circuit is based on current. It's based on moving charges. So, in order to get those charges to move, we have to have something first. What do we need in order to get those charges to start moving? Okay? Katie's that name. Go ahead, Katie.
A battery.
A battery. Okay, so we'll start off with our battery. Okay? First, as far as the battery is concerned, we can talk about a battery as two things. Okay? What else can we consider a battery more generally? Very good. It has an electric field inside of it, but what does that electric field do, Becca?
It provides energy.
Provides energy. So battery could be an energy source, okay? That's how it provides the energy through the field. So it's an energy source, or what else could we call it? Maybe a vocabulary term that's relevant to this unit. Okay? A voltage source. Either one of those will work. Okay? So, we need a voltage source or an energy source. Check. What else do we need if we're going to have these charges moving? Okay? Jump. What? Wire, which is a conductor, right? A place for those charges to move. So, we'll go there. We'll go here. I'll bring it up this way. Actually, I'm going to do that. Then I'm going to do this. switch in. There. And there. Okay. So we got wire, right? What's the important part of the wire? Why do we need the wire? Why do we need the conductor? Okay, that's good.
So the electrons can flow through the circuit
From where to where?
from the battery all the way through to the other end.
Which side of the battery?
The positive to the negative. The negative to the positive.
Because electrons being negatively charged, right? They're going to move away from the negative side towards the positive side. Okay. So in this case, do they have the ability to do that just yet? No, because of the switch, right? But if I close the switch, there it goes. Okay. They caught on fire. Yes. Okay. So, well, let's talk. All right. Becca, good question. Why are they flowing the way that they're flowing? Based on that, based on their flowing, based on the way that they are flowing, can you tell me which side of this battery is the positive side and which side is the negative side? Okay. Hopefully you can, right? Negative side on the right, positive side on the left, because electrons flow from the negative side to the positive side. Is this a circuit? Yeah, it's a circuit. It's not a real good circuit, but it is a circuit. Okay. So let's talk about a couple of terms, and then we'll start talking about this a little more. Okay. So remember the other day when I told you that my PowerPoint got corrupted and there's something wrong with it? This one too, apparently. So black and white, but we're not going to be on slides very much today. We're mostly going to be looking at that picture. Okay. So first, a circuit, by definition, a set of components connected to provide one or more complete paths for the movement of charge. A set of components connected to provide one or more complete paths for the movement of charge. Like we talked about before, circuits have to contain a voltage source or a potential difference source. In the case of our circuit that we just built, that potential difference is coming from where? What's providing the voltage? That's the battery, right? So we said it could be a voltage source or an energy source. That one's closed though.
Yeah, there's a jab towards Becca there.
That really wasn't, I didn't mean that to be a jab. It was just
That was good.
a severe, just a observation.
Don't take it back. Be proud of it. It was good.
Yeah, if you want me to say something mean, I will. I can fix it.
That's alright. Self-esteem's already lowered for today.
Alright, so
Becca has a low self-esteem.
next. Closed circuit, open circuit. Okay? A closed circuit has a complete path of conductors for current to flow from one side of the voltage source to the other side of the voltage source. Where an open circuit has no complete path, there is no place for the charge to flow. Therefore, there is no current. So it has to have a voltage source or an energy source. All right, got those things? Not yet.
Come on, Maddie. Maddie.
So closed circuit, a complete path for electrons to get from one side of the voltage source to the other. Open circuit, no complete path, no charge flow, no current. All right, good there? Okay, so let's talk about a couple of things first. Open circuit, closed circuit. Now, going back to a slide that we've looked at before, this one, right? We've seen this a couple of times. We said, what's the purpose of the battery? What does the battery do for us in this circuit?
Provides the voltage.
So that means that it provides what?
The energy.
Energy. What kind of energy?
Okay.
Electric potential.
Yeah.
Okay? It provides charges with electric potential energy. Then, right? Okay? Then, as this charge moves through the circuit, what happens to that electric potential energy?
Turns to kinetic energy.
Turns to kinetic, but it's not always kinetic though, right?
Thermal energy.
Depending on what's in the circuit, it could be kinetic, that's the current part, or it could be something else, like light and heat, if we're talking about a light bulb, could be like sound, if we're talking about a speaker, but that electric potential energy is getting converted into other forms of energy. The entire time, what is happening to the amount of electric potential energy? It's decreasing until we get
Back to the battery.
back to the battery. Now it has zero potential energy. Okay? So let's take a look first at this circuit. Okay? None of the concepts that we just talked about change here. Those electrons move through the battery and they get a lot of electric potential energy. As they move through the circuit, they have to lose that electric potential energy and turn it into something else. Are there any opportunities to turn that energy into light, heat, or sound in this circuit?
No.
There is not. So the only kind of energy that electric potential is being converted into is what? Kinetic. Meaning, what about these charges?
They go very, very fast.
They go very, very fast. If they go very, very fast, that generally creates friction in those wires. What happens when things encounter friction? They get hot. And if they get hot, now we have a problem.
Fire.
Okay?
He's referring
Now,
to the fire.
Will the wires catch on fire? No. But they will get hot. And if they get hot, they'll start to melt the plastic that is around the wire itself, right? And if it melts through that plastic, then it might like fall through the plastic and onto like paper or wood or something like that. And then what happens? That's where the fire starts, okay? This kind of circuit here we call a short circuit. Okay? A short circuit has very low resistance. If it has very low resistance, that means that all of the electric potential energy that the charges gain from the battery only gets turned into kinetic energy. And if it only gets turned into kinetic, those charges move fast. And if the charges move fast, they get hot, right? A lot of friction, and that's where the heat comes from. And that's where the problems start. So, a circuit with very low resistance. Okay. So, what do we generally do with our circuits? Do we make them so there are only conductors, or really good conductors, from the one side of the battery to the other? No. Right? We do something like this. Open circuit, right? So then,
I have an idea.
and there we go.
It's like the sun.
So now, as far as this circuit goes, okay, do any of the concepts change? What does the battery still do to these electrons? Provides them with electric potential energy. And as those electrons flow through the circuit, electric potential energy get turned into other stuff. What does the light bulb do?
Lights up.
It turns electric potential energy into light, heat, right? As a result, if the light bulb is turning that potential energy into light and heat, how much kinetic energy is left over for those charges? Not a whole lot. Therefore, what do we see about their movement? Not quite as fast. Okay? Does that make sense? Okay. Two things. First, this picture, or this picture, not that picture. Oh, and I didn't even, oh. Stand by. Stand by.
Does anyone actually listen to these?
Once in a while. Gets views.
Does that say single connecting path?
I think you should tell your other classes to.
Yeah, I guess. Oh, it conducting.
So, this picture. First, you have this picture. We've seen it before, yes? Okay. There's something on here that I wish this picture would change. Okay? I would like you to take a minute, discuss with the people around you, how can something about that picture be changed based on what we've discussed up until this point? Small groups, 1 minute, go. I want to change that picture. How do I want to change that picture?
He wants to show the electrons in the picture.
No.
He does not want to show the electrons in the picture. Oh wait, the switch is on.
Nah, that's not. There's something. Oh yeah, sorry. Hold on. Freeze. Freeze.
The arrows in the battery.
Freeze. There is something on this picture that I feel is misleading. That if you don't know better, if you looked at this picture, it might lead you to believe something that isn't true. Okay? There is something about that picture and the way it's labeled that is misleading. Discuss. Go.
Maybe they have to put the little light things around it. Yeah, they'll think the circuit is a certain part right there.
Okay.
The circuit.
Sorry.
I'm out of orange juice.
All right. Okay, so what's the misleading part?
The circuit part, it's went into the wire.
Okay. That wasn't the misleading part I was thinking
Oh
of.
my god.
Okay. At least good.
It's because we don't know if the switch is allowing flow or if it's not allowing flow if we don't know better what
Okay.
to do.
I'll give you that. That's not the one thing I was thinking of.
That's
This is the one part I was thinking of. I did not
battery?
ask that question properly. So, this right here. Okay? If you are watching this at home, you can't zoom in on this, but I can. So, the battery is labeled as what?
Source of electricity.
Source of electricity, right? Okay. If you didn't know any better, and this was labeled as source of electricity, what might you think that the battery does for your circuit?
Provide power.
It provides it with
Electricity.
electricity is moving charges, right? Does the battery provide electrons to the circuit?
No.
No. The electrons are already there. It provides what?
Energy.
It provides energy to those
That was cool.
charges, which causes them to move and do the things that they do. Okay? Next, before we move on to the next part of your notes, is this. All right. Circuit. Moving charges. Lights on. I take the switch and I open it. And the lights go off and the charges freeze. Okay? Your next discussion point. This picture, or this simulator, shows the charges freeze as soon as I open the switch. Okay? Is that what happens? Or, because these charges are gaining energy and they're moving, will they continue moving until the point where the circuit is broken, and we'll end up with a big, like, pile up of electrons right there by the switch? Okay? Discuss. 30 seconds. Go.
Due to the electrons and energy and the
connect the switch, charges flow. I open the switch, charges stop. Honest show of hands in your groups. How many of you discussed that you feel that the electrons would pile up right in front of the switch because that's what they're doing, they're moving, and they'll stop when the brake stops? Honestly, none of you thought that.
No.
Okay.
Still nice, man.
Second, how many of you thought that the charges will freeze immediately where they are and won't move anymore after the circuit gets open? Okay, so out of a class of like 17 or 22, we have 8 people who voted. Okay. How many of you have no idea which one it is?
Well, I said due to the electrons, and that's about all I
So,
said. That's where I got
the correct answer
due to
is
the electrons.
correct answer is those electrons will freeze in place as soon as the circuit is broken. They will not be a pileup of electrons by the switch. How come there won't be a pileup of electrons by the switch, Keenan? They repel each other. You won't have a big collection of electrons right at this point because a bunch of electrons don't like being next to each other. Okay? All right. Are we good with that? Open switch, close switch.
Yes.
Okay.
Already have that one.
Oh.
That's so good.
Hey, for recording class, we're awfully chatty today.
It's Friday.
Yeah, you know what? I don't care.
That scared me because it wasn't until.
So, that picture that we drew up on the board, the circuit that I made for you, is a series circuit. Okay? Because that circuit provides one path for electrons to flow. One path and one path only. Because there is only one path for the electrons to flow, we will see a couple of things. First, the current in every single part of that circuit is going to be exactly the same. Because they all have to go the same path. So we won't have one part that has more electrons than another part. Right, Keenan? Because we just said, what are all those electrons trying to do to each other anyway? Repel. So we won't see a buildup of electrons in one part of the circuit versus another part of the circuit. Okay? Second, the resistance of that circuit, or the impedance to charge flow, how hard it is to get those electrons to flow, is a combination of all of the resistors that are in the circuit, or all the things that are in front of it. Okay? So, if we go back here, right? First, charge flow. Next, the non-contact ammeter. An ammeter measures amps, so it measures current. If I put it, this part here, it's measuring a current of 0.9 amps, right? If I move it here, it measures a current of 0.9 amps. If I move it here, it measures a current of 0.9 amps. The current is the same in all parts of the circuit, okay? Good there. All right. Next thing we're going to do is change this circuit to make it look like this. All right, there's my new circuit. So, two obvious changes to our circuit. Two obvious changes to the circuit, right? What are the two things that we see that happen? Becca, what's one?
The light bulbs got dimmer.
Light bulbs got dimmer. Okay, second one, Sarah.
The amps are moving slower.
Amps are moving slower, right? The electrons are moving slower. Also, if we look at the actual measurement of the current, right, it's lower. How much lower? Half as much, okay? Because now, how many resistors are there in this circuit? There are 2, right? So if I increase the resistance, that's going to make it harder for the charges to flow. That causes the electrons to slow down. Somebody this morning asked a really good question. We talked about that this circuit is basically for the charges to reduce the amount of electric potential energy they have as they travel from one side of the battery to the other. And it reduces that electric potential energy in the terms of light, heat, kinetic, and all those things. Okay? Somebody this morning asked, well, wait a minute. In this circuit, those charges come out of the battery with a lot of electric potential energy. When they get to the first light bulb, they haven't really lost all that much. So how come the first light bulb isn't brighter than the second light bulb? Because the charges have more energy when they get to the first light bulb than when they get to the second light bulb. Okay? Is that a fair question? Yeah. Okay. So the answer is this. If the charges lost all of their energy in the first light bulb, would there be any way for them to get back to the other side of the battery? No. And that's what a circuit is all about. So what we find is that that energy is decreased sequentially as we go through the different resistors, so that it loses a little bit here, a little bit here, a little bit here, so that in the time it gets back to the battery, all of it's gone. Katie, go ahead.
Could we put two batteries in there to balance
Sure.
that?
Sure, yeah. Here, watch this. I got to do it over there. So now, okay, so Katie, let's talk about what's going to happen with the two batteries, right? So, what did we say the battery does, Katie?
It provides energy.
Provides energy to the charges. And then that energy gets converted into light and heat in the light bulbs, okay? Each of these light bulbs converts half of the energy that is provided from the battery, right? So, if I put another battery in there, what should I see with those light bulbs?
They get brighter.
They get brighter. How bright will they be?
As bright as the single.
As bright as the single light bulb. What should I see happen here with my current?
It increases
To what?
to 0.9 amps.
Go for it.
Is this a parallel circuit?
No, this one's still series. Because, actually, Farah, that's a good question. So, it's got two light bulbs, but is this still a series circuit? Why is this still a series circuit? Elise, go ahead. Elise, go ahead. There's still only one path for those electrons to flow. Okay? So far, that's why it's still a series circuit. Alright, so let's put this in here.
That looks fun. Good brighter.
So, Katie, are we good with that?
Yeah.
All the things we predicted would happen happened, right? Okay. Good there? Alright, Farah, let's get to your next question. Okay?
What would happen if it was like all batteries and then like two wires connecting to the light bulb? Would they go really, really fast? Like
Be really, really bright.
You tell me.
Yes? And don't lie either. It's so hot. There's ink all over
Alright. So, two light bulbs. Again, yes?
They're really pretty.
But what do we see now about the brightness of these two light bulbs?
Really bright and it looks like
They're
Christmas.
brighter than they were before. Also, the current that's being measured. What do we read about the current being measured?
Whoa!
3.6, right? So it's twice as much as it was before with the two batteries, okay? So far, this circuit with the two light bulbs is obviously different than the last circuit with the two light bulbs, right? This is what we call a parallel circuit, okay? So the thing that makes the parallel circuit different from the series circuit, a parallel circuit provides multiple paths for charges to flow. Multiple ways that those charges can go from high potential energy to low potential energy. So a circuit that provides multiple paths for current to flow. All right. let's go back to our picture. Sorry, are we done writing this down or no?
I got it.
Go ahead, Farm.
Question over this. When it, in this part, when I was looking at the questions and it said make sure the switch is closed, that the lights, that's where I was curious.
So let's talk where my intention of this, okay? All right. So first, if you go to this junction point, right over here where the first split in the wire happens, what do you see about the electrons? They go either way, right? And if you're following, right, what do you see? It doesn't always happen that way, but they do slow down, yes. But what do you see about how many go this way and how many go that way?
Even every
Not
other.
even, right? Because, Keenan, what are all those electrons trying to do to one another? Now, somebody asked this morning, well, how come a lot of them don't go this way and only a few of them don't go that way? Because if a lot of them went this way, we'd start having a backup of charge, and that doesn't happen. So they split nice and evenly among these paths, although you'll see that if you watch closely, that doesn't exactly happen every time. Okay? But if we look at this light bulb and this light bulb, what are we seeing about how bright they are? They're pretty bright, but in relation to each other, they're exactly the same brightness because each path provides the electrons with a way to get from one side of the battery back to the other side of the battery. Meaning, what has to happen to the potential energy of the charges as they go through these two light bulbs? It has to change energy. By how much? The same amount, because a conductive path, a circuit, has to provide a complete path to get from one side of the battery back to the other side of the battery. Okay? Good there? So if we take our current meter, right, our ammeter, it's measuring 3.6 amps in this part, right? But this part is a common path, right? The two of them come back together here. If I measured the current before this light bulb and the current before that light bulb, what should I probably see? 1.8. 1.8 amps. 1.8 amps.
What did it say before?
Like 3
No, where?
3.6.
Okay.
Okay. Which,
I
does
thought
that
it
make
was
sense?
3.2. Yes, it does.
If I made 3 paths, what would the current in each of those paths read?
Wait, all together?
No, what would each of them read? If I added another light bulb on here.
1.8 was it? What was it? 3.6.
It would read 1.2.
I said
Each
that
of these
first. Why
paths
didn't
would say
anybody
1.
tell me I was
I
right?
didn't tell you we were wrong. Because here, right, Becca,
That's why I was looking.
this is 3.6, right? Oh, if I put another light bulb in here, like right in the middle, okay? If I made it 3 paths where electrons can flow, because right now there's 2, they can go left or they can go straight, right? If I made 3 paths,
Go
a
ahead.
third would go here, a third would go here, and a third would go there, okay? What would we see about the brightness of that light bulb if I put the third light bulb in?
No, the same.
It'd be the same as the other two.
I don't know.
When they're in the other threes.
Well,
Good job, Reese.
Let's try it.
Let's do
Elise
it.
got it. You don't even need to. Elise got it. Right, Elise?
I'm always right about this.
What do you do? Oh, okay. That'll work, I guess.
I wanted to.
You're making us burn.
Wait, that wasn't even. Oh. That was a what?
No.
Whoa.
That would really like to do, but it worked.
It looks like a nativity scene like for Christmas.
No.
Maddie.
It was me.
No.
What do you do?
She admitted to her crime.
It was me. I did it.
Alright,
Don't worry.
so there's my third light bulb, right? Ah, I screwed you guys up, right? Current has gone up now,
Like crazy.
right? Because I forgot about that part. But what do we see about all 3 of the light bulbs, though?
Can I add
Very
it?
bright.
That's good. What is it?
1.8.
Okay.
1.8.
I can read it.
1.8.
Okay,
you said
exactly
1.2.
this. I did. I lied to you. I'm sorry. Okay.
I said 1.8 and
I
you said
forgot
I
about
was wrong.
something.
I was right.
I said I was sorry.
I was only repeating.
All right. Hold on a second. We still got like 6 minutes left. Don't start packing up yet.
We're there.
I don't
Only
give a
got
crap.
6
It's Friday.
minutes.
Finish this. All right.
Tell me when it's 4 minutes.
Don't you know the ambassadors?
So, voltage and current in parallel circuits. The voltage across each component is the same because we said the voltage relates to what?
Battery.
What about the battery? Voltage tells you about the energy of the battery. So, where it says this relates to the, that relates to how much energy is being, how much electrical potential energy is decreasing. Right? That's what voltage relates to. It relates to energy. Either an increase, if you're talking about the battery, or a decrease, if you're talking about turning potential into heat and light, like in a light bulb. But the total current is the sum of the different currents through each component. But what do we see about the current in each part? When we measured the current in each individual path, it's what? It's equal. It's the same as all the other individual paths. The total current being the sum of all those together. All right. Are we good there? The last part of the outline talks a little bit about, hold on a second.
He still has 4 minutes of your attention.
The last part of the outline talks about what happens if I start taking certain wires out. Okay? So, if we go back to this parallel circuit, right? If I remove this wire right here, what's going to happen?
It'll all stop.
They all go out, right? Because that wire is integral for all of them getting back to the other side of the battery. But if I take this wire out, that light goes out, the other two stay on. Okay? Not quite as bright as they were before. No, I'm sorry, bright as they were before. No, not quite as bright. But still go on. Okay? So that gets into the last two parts of the outline that are there for you. Nothing to copy down, but you need to know those things.
Are those batteries up there 9 volts?
Yep.
Can I look one?
Oh, the ones on the table? No, the ones on the table aren't. So,
Oh, well then what? Oh, you thought I was talking about the one in the...
these ones.
That's the one.
There's a person at the door that wants your attention.
Watch this.